Alright, next we're going to talk about the electric field within a sphere with a uniform density of charge. And that would be an insulating material with a uniform density of charge, because we're going to talk about it a little bit later, but the electric field inside of a conductor is 0. Okay, so I'll draw our sphere. So here's our sphere of charge. There's a uniform charge density, so all of the little positive charges are spread out pretty equally throughout the entire thing. Okay. So in the case of a point charge, the radius of the Gaussian surface that we were measuring was way out here. So you could treat this whole thing as just a point charge. But since this is within a sphere, we have to put our Gaussian surface within the sphere. But the radius of this, from the center to the outside, we're going to call that capital R. Alright, and then we can draw our Gaussian surface. The inside. And the distance from the center to that is going to be little r, or lowercase r. But this is an English class, so we can call it big R and little r. Alright, so just like with the infinite line of charge, it's easiest to rewrite the total charge enclosed in terms of density. So I'm going to say that rho equals Q over 4/3 pi big R cubed. This is the surface area of a sphere. Oh, excuse me, this is the total volume of a sphere. And it's the total charge divided by the total volume, and that's important to remember, so I'm going to write it next to it. Over the total volume. Alright, and that comes from the same relationship that we had before. Rho equals the charge over the volume. Alright, so now we have our Gauss's law. And since this is the area integral, we have the surface area of a sphere, which is E times 4 pi r squared, which equals, and we're just going to manipulate this so that we can solve for Q, which equals rho times the volume over epsilon naught. I'm just going to draw a little arrow that shows that that equals Q, because that's essentially what we're doing. We're Q enclosed over epsilon naught, Q over epsilon naught. Alright, now at the point charge this was easy because the total enclosed charge was all of it. But now we have to determine what charge we're enclosing, and that's why this density thing makes it a little bit easier. So we still have the electric field times 4 pi r squared equals, so let's see. So I'm going to rewrite rho just like we determined up here as Q over 4/3 pi big R cubed. So that's rho, total enclosed charge, divided by the total volume. And then since here we have it times the volume, that's just the volume that you're enclosing. So that's going to be times 4/3 pi little r cubed. And then, just like from the original equation, that's going to be epsilon naught. Alright, I recommend that if you missed how I got from this being rho, and then this being just the volume that's enclosed, that you rewatch it, because I didn't understand this the first time that I learned it, and it made Gauss's law really, really hard. So if you can get this, you have the majority of Gauss's law. And this shows up a lot on AP problems, so make sure that you understand how to do it. Good. Okay. So, now that we have it rewritten like that, we can go ahead and divide both sides by 4 pi r squared. Cancel it out. And then we can cancel more stuff out. Yay! So 4/3 goes away, pi's go away, big R cubed stay. This r cubed goes to r squared, as this one goes away. So we're left with E equals Q over r cubed, epsilon naught, 4 pi. Yep. So this is the electric field within a sphere of uniform charge density. And again, those are insulators. Conductors do not have electric fields within them.